Over 90% of the force pulling Andromeda toward the Milky Way comes from mass we have never seen. Why is the most famous galactic collision in astronomy still driven by something invisible? The collision has been treated as a simple future event for decades, but newer measurements are isolating what is actually driving Andromeda toward us. And the answer sits in mass that does not show up in any telescope image. By the end of this video, you will understand what the evidence eliminates from the old explanation, what measurement still has no visible account, and why the motion itself has become a test of whether dark matter exists or whether our model of gravity is incomplete. The core spark is this. Andromeda is moving at 110 kilometers per second toward the Milky Way, successfully fighting against the expansion of space that should be pushing it away. And visible stars account for only a tiny fraction of the pull required to create that speed. What is known is the trajectory and the speed. What is unclear is whether the invisible mass driving it is real matter we cannot detect, or a signal that gravity works differently than we think on galactic scales. What else could create the same effect is a modification to gravitational law at large distances, but that model struggles with other measurements. What would confirm the dark matter explanation is direct detection of the particles, and what would falsify it is finding a gravity modification that matches all observations without requiring invisible mass. Here is one small payoff before we go further. The reason Andromeda does not orbit the Milky Way like a moon orbits a planet is that it has surprisingly little sideways energy, meaning it is moving almost directly toward us, rather than around us. And that low orbital spin is the specific geometric reason the collision is inevitable. Now we can see why the motion is no longer just a dramatic countdown, but a live forensic problem. The old models said galaxies attract each other through gravity. Andromeda is massive. The Milky Way is massive, so they will collide. That explanation is not wrong, but it is incomplete. It does not account for how much mass is required to produce the observed speed, where that mass is located, or why the mass does not appear in visible light. For most of astronomy's history, the collision was predicted without asking what was doing the pulling. The contradictions get dismissed because the merger itself is so visually dramatic that the mechanism underneath seems like a technical detail. The focus has been on what will happen to the stars, the black holes, and the structure of the merged galaxy, not on what is currently accelerating Andromeda toward us. But the first anchor contradiction forces the question open. If you add up all the stars, gas, and dust visible in both galaxies and calculate the gravitational pull they exert on each other, the numbers do not match the observed approach speed. The visible matter alone cannot account for Andromeda moving at 110 kilometers per second toward the Milky Way, while also overcoming the expansion of the universe trying to push it away. The old model predicted that visible mass would be enough. The measurement shows it is not. The micro-reframe is that the collision is not being driven primarily by the galaxies we see, but by invisible halos of mass that extend far beyond the stars. That makes the approach speed not a simple prediction, but a forensic clue about where mass actually lives. A second contradiction appears when astronomers map the scale of the invisible halos. If dark matter were visible, Andromeda's halo would appear 10 times wider than the full moon in our night sky. That means the mass responsible for the collision is not concentrated in the bright galactic disk, but spread across a vast spherical cloud that dwarfs the visible galaxy. The old model treated galaxies as objects defined by their stars. The new measurement shows that stars are only the bright core of a much larger gravitational structure. What this changes is the definition of where a galaxy begins and ends. The boundary is not optical, but gravitational. And the gravitational boundary is already overlapping. The gaseous and dark matter halos of the Milky Way and Andromeda are already touching. That means the merger has technically begun, even though the stellar disks are still millions of light-years apart. The old model treated the collision as a future event with a clear start date. The measurement shows the galaxies are already interacting through their invisible outer layers. The micro-reframe is that the collision is not a moment, but a process. And the process is already underway in the regions we cannot see. A third contradiction comes from the shape of the halos themselves. Mapping suggests Andromeda's dark matter halo is distorted rather than spherical. A spherical halo would produce a symmetric gravitational pull. A distorted halo changes the direction and strength of the force depending on which side is denser. The old model assumed halos were smooth and symmetric. The measurement shows Andromeda's halo is lopsided, which affects exactly how it pulls on the Milky Way and changes the predicted trajectory of the collision. What this reveals is that the invisible mass is not a passive background, but a dynamic structure shaped by previous collisions. Andromeda's halo contains remnants of large galaxies it has already eaten, and those remnants contributed mass that is now pulling us in. The collision we are watching is not an isolated event, but the latest step in a long history of galactic cannibalism. A fourth contradiction appears when astronomers try to measure the motion precisely. For decades, the trajectory was blurred because the Milky Way itself was moving in ways that were not accounted for. The Large Magellanic Cloud is so massive it shifts the Milky Way's position, creating a reflex motion that previously distorted the measurement of Andromeda's path. The old model treated the Milky Way as stationary. The new data from the Gaia Space Telescope tracks the three-dimensional motion of billions of stars and shows the Milky Way is wobbling under the gravitational influence of its own satellites. Once that wobble is removed, the trajectory becomes clearer. What this changes is the confidence in the prediction. The collision is not just likely, but geometrically locked in, because the corrected measurement shows Andromeda has even less sideways motion than earlier estimates suggested. A fifth contradiction comes from the role of large-scale structure. Both galaxies are traveling along a massive filament of the cosmic web, a dark matter structure that guides them toward each other like a highway. The old model treated the collision as a local two-body problem. The measurement shows the motion is embedded in a larger flow of matter along invisible cosmic scaffolding. The filament is not made of stars or gas, but of dark matter, and its gravitational pull funnels galaxies together over billions of years. What this reveals is that the Andromeda approach is not random, but part of a coordinated pattern of motion shaped by the largest structures in the universe. A sixth contradiction appears in the dynamics of the halos themselves. As the halos overlap, they create a gravitational wake that acts like a drag force, slowing the galaxies down and ensuring they merge rather than passing through each other. This effect is called dynamical friction. The old model assumed galaxies would either collide or miss based on their initial velocity. The measurement shows that even a near miss would be converted into a collision because the halos interact and bleed energy. What this changes is the inevitability of the outcome. Escape is impossible. Even with sideways motion, the mutual gravity of the two galaxies is too powerful to overcome. A seventh contradiction comes from the environment around the local group. The local void, a vast empty region behind the Milky Way, is expanding and physically pushing our galaxy toward Andromeda. The old model treated voids as passive empty space. The measurement shows voids exert pressure by expanding faster than the average universe, creating a push that adds to the pull from the opposite direction. What this reveals is that the collision is being driven by both attraction and repulsion, and the motion is a result of the full three-dimensional gravitational landscape, not just the mass of the two galaxies. An eighth contradiction appears in the timeline itself. Billions of years ago, the two galaxies were moving apart with the expansion of the universe, until gravity finally halted them at a specific point called the turnaround point and pulled them back. The old model treated cosmic expansion as the dominant force everywhere. The measurement shows there is a mathematical boundary around the local group, called the zero-velocity surface, where gravity officially defeats the expansion of the universe. Inside that boundary, galaxies collapse together. Outside it, they recede. What this changes is the understanding of where expansion ends and gravitational collapse begins. The Andromeda approach is not a violation of cosmic expansion, but a local exception carved out by concentrated mass. A ninth contradiction comes from testing the model itself. The Andromeda approach serves as a real-world laboratory to test if dark matter exists, or if our understanding of gravity is wrong. If the motion can be explained by modifying the law of gravity at large distances, then dark matter is unnecessary. But modified gravity models struggle to match the observed motion without also breaking predictions in other systems. The old model assumed Newtonian gravity with visible mass. The measurement forces a choice. Either add invisible mass or change the law of gravity. What this reveals is that the collision is not just a prediction, but a test, and the test is still open. Streams of stars torn from smaller galaxies act as gravitational breadcrumbs, tracing the shape of the invisible mass between the two giants. These tidal streams follow paths determined by the distribution of dark matter. If the dark matter map is wrong, the streams would follow different curves. The old model could not predict these streams without knowing the halo shape. The measurement of the streams now constrains the halo shape, and the shape matches the dark matter prediction better than the modified gravity prediction. What this changes is the confidence in the dark matter explanation, but it does not close the case because other explanations are still being tested. So, what does the evidence eliminate, and what does it leave unexplained? The evidence eliminates the possibility that visible matter alone is driving the collision. The approach speed, the halo size, the dynamical friction, the tidal streams, and the zero-velocity surface all require more mass than we can see. The result still has no direct account for what that invisible mass is made of. The mechanism is strongest if dark matter is real, but the particles have never been detected in a lab. The interpretation remains open because modified gravity has not been fully ruled out, and the possibility that we are misunderstanding gravity at galactic scales is still unresolved. What this verdict changes for your understanding is that the Andromeda collision is no longer just a future spectacle, but a present-tense forensic problem. The motion we measure today is a clue about the structure of space, the distribution of mass, and the limits of what we can see. The galaxies are being pulled together by something that fills more volume than all the stars combined. And whether that something is real matter or a gap in our equations is the question the collision itself is helping to answer. The approach is not just inevitable, it is diagnostic, and the diagnosis is still incomplete.